Forgotten navigators. How longitude shaped early maritime empires. For most of human history, sailing across the open ocean was an act of courage mixed with uncertainty. Once land vanished beyond the horizon, sailors entered a world with no road signs, no landmarks, and no reliable way to know where they truly were. Ships could drift for weeks without realizing how far east or west they had traveled. This single mystery, longitude, shaped the fate of empires, decided wars, and cost thousands of lives. Today, longitude feels simple. It is just a number on a map or a coordinate on a phone screen. But for early navigators, longitude was one of the greatest scientific and engineering challenges the world had ever faced. Latitude was easy, longitude was not. Finding latitude, how far north or south you are, was relatively straightforward. Sailors could measure the height of the sun at noon, or the position of stars like Polaris. The Earth does not rotate north to south, so latitude remains stable and predictable. Longitude was different because the Earth rotates east to west. To understand longitude, sailors had to understand time. The Earth spins 360 degrees every 24 hours. That means it rotates 15 degrees every hour. If a sailor knew the exact time at a fixed reference point, such as their home port, and compared it to the local time on their ship, they could calculate how far east or west they were. Here is the key idea. Local noon is the moment when the sun is at its highest point, in the sky where you are. If it is local noon on the ship but the clock set to the home port reads 200 p.m., the ship is behind home time and therefore west of its home port. 2 hours multiplied by 15 degrees equals 30 degrees of longitude. If the home clock instead read 10 a.m., the ship would be ahead of home time and therefore east. The math was simple. The problem was the clock. When longitude errors turned deadly. No clock in the early 1700s could keep accurate time aboard a ship. Pendulum clocks failed on rolling decks. Springs expanded in heat and contracted in cold. Salt air corroded metal. Even a small error, just seconds per day, could place a ship dozens of miles off course after a long voyage. In 1707, this uncertainty led to catastrophe. A British naval fleet under Sir Cloudesley Shovel was returning home at night after a long campaign. Believing they were safely in the English Channel, the ships instead smashed into the rocks of the Isles of Scilly. 4 warships were destroyed and nearly 2,000 sailors were killed. According to later accounts, one sailor aboard the fleet had carefully kept his own reckoning and tried to warn Admiral Shovel that they were dangerously off course. The warning was ignored, and legend holds that the sailor was hanged for mutiny on the spot. Whether fully true or not, the story captures a haunting reality of the age. In a rigid naval hierarchy, a low-born sailor was not permitted to contradict official navigation. Longitude was not just a mathematical problem. It was a problem of authority and class, a prize for the impossible. The disaster shocked Britain. Parliament responded with the Longitude Act of 1714, offering a reward of £20,000, a fortune worth millions today to anyone who could devise a practical way to determine longitude at sea. To judge the solutions, the government created the Board of Longitude, made up largely of astronomers and scientists. Most believed the solution lay in the heavens. The leading contender was the lunar distance method, which involved measuring the angle between the moon and certain stars. Because the moon moves in a predictable way, these measurements could be used to calculate time differences and therefore longitude. In theory, it was elegant. In practice, it required clear skies, complex calculations, and extraordinary precision, hardly ideal in storms or darkness. As the years passed with no solution, desperation grew. Wounded dogs and desperate ideas. Some proposals bordered on the absurd. One infamous idea involved the so-called powder of sympathy. According to this theory, a dog aboard a ship would be wounded, while a person on land treated the knife or bandage with a magical powder at a specific time each day. The dog, supposedly connected across distance, would yelp at that exact moment, signaling the correct time to sailors at sea. Other schemes suggested firing cannons on schedule from coastal stations or anchoring ships across the ocean as reference points. None worked, but they reveal how urgently the world needed longitude. The carpenter who challenged the experts. While astronomers debated, an unlikely challenger stepped forward. John Harrison was a self-taught carpenter from Yorkshire with an obsession for clocks. He believed longitude could be solved not with stars, but with engineering. If a clock could keep accurate time at sea, longitude would become a simple calculation. Over decades, Harrison built a series of increasingly refined timekeepers. H1 1735 was massive, filled with brass and weighing about 75 pounds. It looked more like a machine than a clock, but it proved something revolutionary. A timekeeper could survive at sea. H2 and H3 improved on the idea, addressing motion and temperature problems, though they remained large and complex. H4 1761 was the breakthrough. Just 5 inches wide, it resembled an oversized pocket watch. H4's success was not accidental. It relied on two key innovations: Harrison's grasshopper escapement, which reduced friction almost entirely, and bimetallic strips, which automatically corrected for temperature changes. Together, they solved the very problems that had defeated every sea clock before. To the board of longitude, however, H4 looked almost toy-like compared to the massive machinery of H1, deepening their skepticism. Victory without celebration. When H4 was tested on a voyage to the Caribbean, it lost only 5 seconds over 81 days. For the first time in history, sailors could trust their longitude. Yet the board of longitude hesitated. The leading advocate of the lunar method, Neville Maskelyne, was both the Astronomer Royal and a member of the board, meaning he was judging Harrison's work while promoting a competing solution. The result was years of delays, additional tests, and shifting requirements. Only after appealing directly to King George III did Harrison receive most of the prize money, and even then, not as a formal award. He was in his 80s. Longitude, it turned out, was as much about politics as it was about precision. How longitude reshaped empires and the global economy. Once marine chronometers became reliable and affordable, the seas changed forever. Before chronometers, ships relied on parallel latitude sailing to a known latitude and then running east or west until land appeared. These routes were slow, predictable, and dangerously exposed to pirates and enemy fleets. Chronometers enabled great circle routes, the shortest paths across the globe. Voyages became faster, safer, and cheaper. Insurance costs dropped, trade accelerated. In a very real sense, the chronometer shrunk the world. The final proof came during Captain James Cook's second voyage. Cook carried a copy of H4 made by Larkham Kendall, known as the K1. In his journals, Cook praised the watch repeatedly, noting that it never led him astray. His reports convinced sailors worldwide that the clock method had decisively beaten the lunar one. Britain, which adopted the technology early, gained a decisive advantage, helping secure its place as the dominant maritime empire of the age. From the sea to the digital age. Longitude eventually required a universal reference point. In 1884, nations agreed on the prime meridian at Greenwich, England. From it came Greenwich Mean Time and later Coordinated Universal Time, UTC, the foundation of modern global timekeeping. Today, the very room at the Royal Observatory in Greenwich, where Neville Maskelyne once championed the lunar method, now houses John Harrison's clocks, H1 through H4, still ticking centuries after their creator's victory. Longitude still depends on time. A GPS satellite is essentially a very fast-moving clock in orbit. If its internal clock were off by just 1 microsecond, your position on Earth would be wrong by roughly 300 meters. Modern navigation still rests on the same principle. John Harrison proved centuries ago. The legacy of the forgotten navigators. The story of longitude is not just about clocks or calculations. It is about persistence, imagination, and the courage to challenge authority. It reminds us that progress does not always come from prestigious institutions. Sometimes it comes from a quiet workshop, and a refusal to accept that a problem is impossible. Every time a ship docks safely, a plane crosses an ocean, or a phone finds its location, it echoes the emphasis of forgotten navigators, who finally learned to measure the invisible. Longitude may be just a line, but it changed the world.
It's time to study new words in context. 1. A pendulum. Definition. A pendulum is a weighted object that swings back and forth, often used in early clocks to keep time at a steady rhythm. Example: the pendulum stopped swinging when the ship rolled in heavy seas. 2. Corroded. Definition: corroded means slowly damaged or eaten away by chemical reactions, especially caused by water, air, or salt. Example: the salty sea air corroded the metal parts of the clock. 3. Catastrophe. Definition: a catastrophe is a sudden and terrible event that causes great damage, suffering, or loss of life. Example: the shipwreck was a catastrophe that shocked the entire nation. 4. Reckoning. Definition: reckoning refers to the process of calculating or estimating something, especially a ship's position based on past movement. Example: the sailor trusted his own reckoning rather than the official charts. 5. Hierarchy. Definition: a hierarchy is a system in which people are ranked, according to power, authority, or social status. Example: in the naval hierarchy, ordinary sailors were expected to obey officers without question. 6. Some proposals bordered on the absurd. Definition: this phrase means that certain suggested ideas were almost ridiculous, strange, or unreasonable, even if they were taken seriously at the time. Example: some proposals bordered on the absurd, including plans that relied on magic instead of science. 7. Yelp. Definition: a yelp is a short, sharp cry, usually made suddenly because of pain or surprise. Example: the dog let out a loud yelp when it was startled. 8. Breakthrough. Definition: a breakthrough is an important discovery or achievement that solves a difficult problem or leads to major progress. Example: Harrison's clock was a breakthrough in navigation history. 9. Grasshopper escapement. Definition: a grasshopper escapement is a low-friction pendulum clock mechanism invented by John Harrison that uses two hinged pallets to impart energy to the pendulum, allowing for highly precise timekeeping by reducing wear and friction. Example: the grasshopper escapement helped the clock keep time, even on a moving ship. 10. Chronometer. Definition: a chronometer is a highly accurate clock designed to keep precise time, especially under difficult conditions like those at sea. Example: the ship relied on a chronometer to calculate its longitude. 11. Astray. Definition: astray means off the correct path, or away from the intended direction. Example: without accurate timekeeping, ships often went astray in open waters. 12. Maritime. Definition: maritime relates to the sea, ships, or activities connected with ocean travel and navigation. Example: Britain became a powerful maritime nation during the Age of Exploration. 13. Prime meridian. Definition: the prime meridian is an imaginary line at 0 degrees longitude that serves as the global reference point for measuring east and west. Example: all time zones are calculated using the prime meridian as a starting point. 14. Championed. Definition: championed means strongly supported, defended, or promoted an idea or cause. Example: the astronomer championed the lunar method over mechanical clocks. 15. Persistence. Definition: persistence is the quality of continuing to work toward a goal, despite difficulties or opposition. Example: Harrison's persistence allowed him to succeed after many years of failure. 16. Prestigious. Definition: prestigious describes something that is highly respected and admired because of its importance or reputation. Example: the prestigious scientific board was reluctant to accept ideas from an unknown carpenter.
Comprehension questions. 1. Why was navigating the open ocean especially dangerous before the 18th century? Answer: because sailors had no reliable way to know how far east or west they were. which often caused ships to become lost or crash into unseen land. 2. What is the difference between latitude and longitude? Answer. Latitude measures how far north or south a location is, while longitude measures how far east or west it is. 3. Why was latitude easier to calculate than longitude? Answer. Latitude could be calculated using the sun or stars, which stay relatively fixed, while longitude required precise timekeeping, because the Earth rotates east to west. 4. What does local noon mean? Answer. Local noon is the moment when the sun reaches its highest point in the sky at a specific location. 5. How does time help sailors calculate longitude? Answer. By comparing local time on the ship to the time at a known reference point. Sailors could calculate how far east or west they had traveled. 6. Why did early clocks fail at sea? Answer. Because ship movement, temperature changes, and salt air caused clocks to lose accuracy. 7. What happened during the 1707 Scilly naval disaster? Answer. British warships misjudged their longitude and crashed into rocks near the Isles of Scilly, killing nearly 2,000 sailors. 8. Who was Sir Cloudesley Shovel? Answer. He was the British admiral in command of the fleet that was destroyed in the 1707 Scilly disaster. 9. What legend highlights the role of authority and class in the Scilly disaster? Answer. A sailor reportedly warned that the fleet was off course, but was ignored, and possibly executed, because he was not allowed to challenge official navigation. 10. What was the Longitude Act of 1714? Answer. A law passed by Britain offering a large reward to anyone who could find a practical way to measure longitude at sea. 11. What was the Board of Longitude, and what did it believe? Answer. It was a government group created to judge longitude solutions, and it believed astronomy, not clocks, was the best approach. 12. What was the lunar distance method? Answer. A technique that used the moon's position relative to stars to calculate longitude, requiring complex calculations and clear skies. 13. Who was Nevil Maskelyne, and why was he controversial? Answer. He was the astronomer royal and a supporter of the lunar method, who also judged John Harrison's work, creating a conflict of interest. 14. What was the powder of sympathy proposal? Answer. A belief that a wounded dog aboard a ship could be magically connected to land, yelping at set times to signal longitude. 15. Who was John Harrison, and why was he important? Answer. He was a self-taught carpenter who solved the longitude problem by inventing an accurate sea clock. 16. What made Harrison's H4 chronometer revolutionary? Answer. It was small, extremely accurate, and reliable at sea, losing only seconds over long voyages. 17. Why did the Board of Longitude hesitate to reward Harrison? Answer. Because they distrusted mechanical solutions and favored astronomical methods. 18. How did chronometers change global trade and empire building? Answer. They allowed faster, safer routes, reduced costs, and gave maritime powers a major economic and military advantage. 19. What role did Captain James Cook play in proving Harrison's invention? Answer. He used a copy of Harrison's chronometer on a long voyage and confirmed its accuracy through real-world navigation. 20. How is longitude still important today? Answer. Modern systems like GPS depend on precise timekeeping, using atomic clocks to determine location.